Well, I'm Victor. Well, 7 years ago, I was here in AstroCamp as alumni, and now I'm going to present my bachelor thesis because I finished my physics degree 3 weeks ago, and it was a project that I have been working on, I don't know, the last 10 months, trying to understand a little bit the main effect that we are going to talk about, the theme of that is the chromatic surface brightness modulation. Also, I focus on creating a methodology to study how the galaxies change with the redshift. That I know that you know how is the redshift now, so for me it's going to be more easy this presentation. Okay. Well, these are all the contents that I'm going to talk about. There are a lot, but I think there's not just one equation. That's one equation, so don't be worried about that. But what is the main object of the study on this project is the galaxies, and how can we define a galaxy? Astronomical object formed by stars, by planets, by dust, by gas, and dark matter, all then bounded by gravity. Usually, it has a mass greater than 10 to the 6 solar masses. And here we can see the typical picture of a spiral galaxy. Also, it's not the only one because all these points of light are also galaxies that are farther away, except this one and this other, because we have peaks. So these are stars, because the stars in our Milky Way produce this kind of peak. So when you see an image of a galaxy, you have to take into account that this kind of objects are stars from our Milky Way. But the rest are galaxies. There are a lot of galaxies, even more than we can see in this screen. Galaxies usually have the different shape because there are billions of galaxies, so everything are more or less the same, but they have a different shape. For example, here we have an elliptical galaxy, here we have a spiral galaxy, and there we have a penguin galaxy. Well, it's a irregular galaxy with the shape of a penguin. Also, this one is a elliptical galaxy like this one. So as you can see, there are some difference between the morphology of the galaxy, and of course we need a classification of this object because everything in astronomy has their own classification. The stars and galaxy is the same. It was Hubble in the past century who started to create a system to classify these galaxies. So he create a diagram like this, in which we have different morphologies for the galaxies. For example, here we have the elliptical galaxies. Also, they called early-type galaxies because it was believed that the first galaxies to form was this, and then the evolution to that. But it was not true because we find some other galaxies, spiral galaxies, other than elliptical galaxies. So the elliptical galaxies are like balloons, like spheroids, but they are projected in 2 dimensions because we just see the sky is like this screen is 2-dimensional. So we cannot see the entire shape. It's not like a rugby balloon, it's just 2 dimensions. But also we have another different kind of galaxies that are the spiral that we can divide in 2 types. The normal or unbarred spirals, and we have the barred spirals. Why? Because we can see here that we have a bar of matter that is crossing the center of the galaxy. These spiral galaxies are formed by 2 parts. In the center, we can have a bar and a disk. I can see here. Okay. This is a spiral galaxy. We can see here that is a disk. This is the edge of the disk. What happens in the other cases that we just see just the face, so we don't see the edge, just the face. But in which one the galaxy, the shape will be like this. And also we have in the spiral galaxies, we have like a center that behaves like a elliptical galaxy. So A spiral galaxy is very complicated because we have a mixture of elliptical galaxy and a mixture of other things like this. So we have to understand this part separately, and this part will be bright differently. So we say that the different parts of the galaxies are two types of stellar population. We have two main times because we can subdivide it, but the main ones are the type 1 are the youngest stars, and they are blue. As you can see, it's formed in the arms of the spiral galaxy. You can see here that these arms are bluer than the center that is red. That's because here in the center we have the type 2 stellar population that are all the stars have a great low metallicity because metallicity increases the blue color, and the center is like elliptical galaxy. It's like elliptical galaxy, and just we have the disk with the arms. So blue in the disk and red in the center. And this is important to different because, as I told you, they bright in a different way. And how we can study the bright with this kind of equation is the Sersi profile in one dimension. This expression is very simple. It's just an exponential function with a lot of some parameters that tell us how the bright of a galaxy behaves with the distance. We have important parameters that are this one, the effective radius, that tell us if we take the entire light of a galaxy, and we take just the half of that galaxy of that light, the radius that contains this area that divides the half of the light of a galaxy is the effective radius. So it's like a measure of the size of the galaxy, but it's just mathematical. So we are trying to improve these measurements of the effective radius with other methodologies. Also, we have a Sersi index. That this is very important parameter because low Sersi index indicates that we have a disk of a spiral galaxy. So the bright of the galaxy is compared to the bright that produces a disk of a spiral galaxy. But if we have, for example, greater in Sersi index, we are talking about the center of an elliptical galaxy. So behaves different. It's not the same to see a galaxy that is like a balloon, like see a galaxy that is like a plain disk. So it's very important to know this value. And that's one of the parameters we focus on this study. And the other are, well, the intensity at a distance, the effective radius, and another parameter that depends on n. Well, these are maths, but how it looks. These are the values for the Sersi index. We see, we increase the Sersi index, the brightness in the center, that is the intensity of the profile, is bigger than the other parts. And also when the Sersi index is greater, we have a smoother transition from the highest part of the galaxy to the low intensity of the galaxy. This is the center of the galaxy, so we are just going to the extreme of the galaxy. This, the Sersi index, this one, well, the Sersi profile is a generalization of the Freeman profile and the Bakuler's profile. So the past century we used two, but now we have an option to create one model that represents all the galaxies, and this is very, very useful. But now I'm going to talk about how we obtain the data in which we work. So there are three main techniques to obtain data from the galaxies. The first one is the photometry, and what produces the photometry is an image. Every image of the galaxy is just, we have here the galaxy, the light travels, so optical system, and then arrive to the sensor. These are CCD sensor, the same as you have in your mobile phone, in your camera, but it's so much. It's better, it's more accuracy. And that is the photometry. Photometry creates an image. What happens with the spectrometry? with the spectroscopy, we need things like that, a prism that separate the light, the wavelength of the light in its color. So between, we have here the galaxy, the telescope, the optic system. We have this one that scatters the light, that creates a rainbow, and that this light arrives to the sensor. So knowing how is the intensity of the pixel of the sensor, we can derive the spectra. But the most important one, or the one that we use, is the 3D spectroscopy. Why is 3D? Because we have the combination of the photometry and the spectroscopy, and we create something like this, a data cube. Because what is a data cube? Because we have here the 2 dimensions of an image, and we have also the third dimension that is the spectra. So here we have the wavelength, and each pixel of the image has a unique spectrum. So these data are obtained with this instrument, that is the MUSE instrument, that is located in the very large telescope. Carlos gave us some stats of with these telescopes, and is very important, and is part of the ISO observatory. So it's one of the most important scientific instruments that we have actually to see the galaxies. Okay, now let's talk a little bit about Redshift. You know now a little bit of Redshift, but what is Redshift? Well, Redshift is like a measurement, is like a way of measure distance in astronomy, because the universe is in constant expansion. So it's not useful to say, okay, now this is 1 meter, because probably, I don't know, 2 days later, this is not a meter, this is less than a meter, because the universe is in expansion. So we prefer to talk about redshift. So the farther apart two galaxies are, the faster they separate. So, for example, if I have a galaxy near here, we are going to separate lower, or slower than if we are here. So that's a very fundamental part, because the redshift is not linear. For example, if a galaxy separates 1 unit from another one, that does not say that if another 2 galaxies are separated 2, the redshift will be 2. So it's not linear with distance, and this is very important. And like you know, the redshift produces an increase of the wavelength. So mathematically, it's like that. This is redshift, okay? And we have here that this is the wavelength that we observe in our telescopes, and this is the wavelength that is emitted by the galaxy. So we can say that the wavelength observed is always bigger than the wavelength emitted, because we have a factor that is theta, and theta is always greater than 0 if we are talking about the universe expansion. For example, if we tell that two objects are closer, well, theta will be negative, but not it is the cosmological expansion. Always that is a cosmological expansion, theta is greater than 0. That's why always the wavelength observed is always greater than the wavelength emitted. And this is produced in this spectra. For example, we have the emitted spectra, and we will observe this spectra. So these are the absorption band, and we know that this will be restricted to the greater wavelength. And this is very important, because we measure all the galaxies with different filters, because, for example, when you see a galaxy that is a lot of colors, well, this is a mixture of different filters in the green band, the blue band, and the red band, because we cannot pretend to obtain the huge, the entire spectrum of the light that you produce. So we use different filters for each telescope. This is the case of the Euclid telescope. And what happens? Well, we obtain an image of a star that is represented that star, the black star, but that's a redshift 0.5. But what happens that if we want to measurement the same star that is farther away, is redshifted? Well, then the wavelength is increased. And what happens that in this range, the blue filter is not enough, because our star is not here. So if we try to measurement the star with the blue filter, we are not going to see anything because it's not emitted in this band. So we need to change the filter, and this progressively with the if we increase the redshift. So it's very important to know that this happens because if not, you can probably see things that are not correct. But the redshift is the change in the wavelength is not the only thing that produces the redshift, because also redshift produces a decreasement of the intensity of the light with this factor. And we can see here that if we take redshift 0, we have almost 7,000 counts. This is an intensity. But if we take redshift 3, we just have 26 counts. So we are receiving 7,000 photons, and now we are receiving just 26 photons, just with a 5, with 2 steps of redshift. We decrease into a magnitude order the amount of light that we have. So this is very important, because probably if you take a photograph of in the first case, just with 1 second of exposure will be enough. But for example, in this case, we need, I don't know, probably 30 minutes, 30 seconds to obtain the same amount of light than in the first case. And here we can also see the other effect, that is the expansion of the wavelength, because here see that we have just a 2000 range of wavelength, but in this case we increase to 10,000 wavelength. So this is an expansion of the wavelength, just because we see in the previous image that they also is restricted to a greater wavelength. And this is what TMOD, that is this effect, is trying to study. How is changed everything, how changed in the, for example, take this into account. The red are like elliptical galaxies like balloons. And the blue dots are like disks of a spiral galaxy. Well, as we can see here, the dominant light is from the elliptical galaxy, because we have 7,000 counts, and in this range, this is what is the dominant. But what happens here? That in the same range, we take range of this one is the blue. So we have a transition between a galaxy looks like a balloon into a galaxy that looks into a disk, and this is not different object. This is probably the same object that is work restricted. So we are not changing the morphology in the galaxy, because the galaxy is always a spiral or always is a elliptical. We didn't change that, but we changed the way in which we see it. It's like, what is the truth? The truth is the first case, or the truth is the other case? It's a disk, it's elliptical, we don't know. So this is what Timotefes is trying to study. How is changed this between elliptical galaxy into a disk galaxy. And how we study this? Well, we create using Python, we create from scratch an entire process that took 10 months of code. And we start with the data types. These are created with news data, but we want to modelize. For example, this image was with news, but we want to know how will be seeing that galaxy with the Hubble Space Telescope. That's why we need the spectrum, because we want to modify the spectrum in a way that we can see, okay, this galaxy is simulated in the Hubble Space, in the telescope, in the James Webb, or in the Euclid. So we did that simulation. Then we need to obtain this image. This image is the point spread function that you say is like, well, it's just like a circles. But this is very important, because this image contains all the scattering that light suffer when they come from the galaxy to the telescope. For example, the atmosphere of the Earth modifies the light. So with this image, we can obtain all that modification, and we can apply to the original image to have like a perfect image of the galaxy. So it's very important to know how the modification produced by the atmosphere looks like. And that is the point spread function, and it's very, very important image. And this one are the simulated galaxy. In this case, is a simulated image that we took from this data cube in Muse, and we simulate like it was an image of the Hubble Space Telescope. Okay, the colors are arbitrary because they show that the brightest part, the white part, has more intensity than the blue part, but it's not a real color image. But this was like a simulation from one telescope to another telescope. And then we applied a GALFIT. That GALFIT is a program that took all the parameters that we see in the Cersei profile, the effective radius, the Cersei profile, and we try, GALFIT tried to fit all that parameters. So GALFIT takes one effective radius, takes one Cersei index, combined them, and took a model of a galaxy. This is a model of a galaxy that we obtained with GALFIT. But GALFIT say, okay, this galaxy looks like the other one. Yes, no. So if the error of the model with respect to the original image is big, GALFIT will try another set of parameters. We'll try another effective radius, another Cersei index. So GALFIT will take as output the best model possible for the first image. But are things that we have to take into account because, well, this was the first result we obtained with GALFIT. As you can see, it's like, okay, why we have these spikes? It's not normal because we know that physics is not like random values. It should be look like the other one. Well, this one of the fact that we have to take into account when we are working with programs like GALFIT that tries different sets of parameters, because GALFIT tries to fit to the minimum value, to the perfect value, to the perfect model. Okay, but they have a lot, infinite values for proof. So just GALFIT just return as maximum 100 of iteration, 100 of possible models. So when it didn't find, when GALFIT doesn't find the first one, returns random values. What happens there? That we introduce, for example, if we find a minimum in the parameters, so we know that the model is the perfect model, we can say, okay, that model will be the input for the next image because it's a simulated image. We have 109 image simulated different frequency from 00 to 5.4. So we took that model and we introduced like the input model, and that's what changed between the two images. But it's not just the result, because for simulate this galaxy, it took 17 hours. Simulate just one galaxy. With the other, with the other plot, we took 2 hours of parameters. So we have a sample of 15 galaxies that each one took almost 1 day. It will be 1 month to analyze, half month to analyze all of them. But now with that method, we can analyze all of them in just 48 hours. And these are the set of 15 galaxies we analyzed. Those are the beautiful image, RGB colored galaxy, but the data we have, the astronomers, is not that beautiful, but I prefer to show you that really look like. For example, we have elliptical galaxies, we have a spiral galaxy. It's a combination of all the morphologies that we can find. But Muse is very special because it just have one arc second of field of view. So we just focus on the center of its galaxy. Well, these are the parameters. For example, when we have S, we have a spiral galaxy. AB is that is between a barred galaxy and unbarred galaxy. For example, when we have E is a elliptical galaxy, that's how the astronomers call the different galaxies. And then we have the redshift. They are very close to us. When redshift is near 0 or almost 0, we are talking about the local universe. So we take a galaxy from near us, and we are going to simulate that this was very far away, because 5.4 is very, very far away from us. These are all the filters that we have simulated because every galaxy had simulated just not in one telescope, also in the entire set of filters that we have there. That's why we took almost 17 hours in the first case to analyze all of them, because there are, with these all things, with the 15 galaxies, we simulate 45,000 galaxies, and we analyze them individually. And these are the results. Well, this is not an important parameter because it's the center of the galaxy, but these are how the plot looks like. We have here the redshift that I talked about. So we have 0 redshift, this is local universe, and we have 5.4 redshift. So we are simulated in distance. And this is the emitted wavelength. What is this? Each filter has a reference wavelength. In this case, is 1,500 nanometers. So this is the wavelength that a galaxy should emit if we are going to see it with this wavelength, this reference wavelength. So there is a transition suffering the redshift from, okay, originally the galaxy emit in this 200 nanometers, and we are going to receive in 1,500 nanometers. That's what represents this axis. And now we have the X center position in blue, and in orange we have the Y center position. But it's not the most important parameters. The most important parameters are these two ones, the Celsius index. And what is happening here? For example, in this filter, we have a value of 4. A value of 4 is like elliptical galaxy. And we finalize the analysis with a value of 1. So we have a transition between something that looks like an elliptical galaxy into something that looks like a disk of a spiral galaxy, but it's the same galaxy. It's the same galaxy. It's just, we see it different, but the mass of the galaxy, the components of the galaxy are always the same. What happened? That light change with distance, so we see the object different. But what is the truth? The truth is that it's an elliptical galaxy. The truth is that it's a spiral galaxy. No, it's just the same. There are different ways in which we can see it. And this is the evolution of the effective radius, the size of the galaxy. We can see that, for example, this is this galaxy that is a elliptical galaxy. We see that the effective radius always increase with the time. So we represent another kind of plot that, for example, this one that represents the ratios between, in this case, the static index, between the reddest filter that are our reference filter, and also with the initial value. So we can see here some behaviors of the plots, and this one also for the effective radius. And we can see here that, for example, in red we have that always increase the value. So the initial value of the effective radius is always the smaller one. So we know with this one that is always increasing, but never is twice bigger than the initial value. So the galaxy doesn't grow too much. And these are more results. This is for elliptical galaxy with different behavior. This is for another elliptical galaxy, and we can see here a different behavior from the previous one. For example, there in the effective radius that changed the green line. Well, that looks very different from one kind of galaxy to another kind of galaxy. So we are trying to know how can we put this into a mathematical model. So for summarize, the main object, the main goal was achieved because we create a automatical system that analyze individually more than 45,000 images. That is a lot, and it's the first time that someone do this with the Azimuth effect. And we are trying to understand the physical consequences of everything I told you, the transition between one kind of galaxy to another kind of galaxy. We need to obtain the errors of the results because we don't know how accurate they are, but there is a complex process because there are a lot of images to simulate. We need to create a bigger sample of probably, I don't know, 50 galaxies with more morphologies. But for me, and for you, because you are still young, this is the more important conclusion because it's not just everything is about astronomy. For this project, I need optic, I need electronic, I need quantum mechanics, I need programming. So it's not like, yes, you like astronomy, but you have to know everything about the physics to trying to understand just a single part of the astronomy. So be so the knowledge that you acquire, for example, in optic or in electronic, that is very important because you never know when it's going to be very useful. And also ask questions to concepts because all this starts with a question that we are measuring the really size of the galaxies. We are knowing the truth of the galaxies is elliptical, is a spiral galaxy, and this question creates a lot of papers, this project, and in the future will be more of that. So that's everything. Thank you for your attention. And if you have a question, or you want to see more images of galaxies, or like the penguin.